Assalamu alaikum class. In today's lecture we will move forward toward our next topic, tree data structure. The data structures that we have discussed in previous lectures are linear data structures. For example, arrays, linked lists, stack and queues. In these data structures, the elements are in a line and we put and get elements in and from a stack in linear order. There are a number of applications where linear data structures are not appropriate. In such cases, there is a need of some non-linear data structure. Tree is the example of non-linear data structure. To get better understanding how tree data structure look like, let's see the hierarchy of the family, in which the node at the top of the tree is Muhammad Aslam Khan, the head of the family, and there are three nodes under this one. These are Suhail Aslam, Javed Aslam, and Yasmin Aslam. And then there are nodes under these, and these nodes are the son and daughter of these three family members. You can make the tree of your family too. Notice that this tree is not like a linear data structure like linked list. And this tree is in a top down form in which the father of the family is on the top with their children downward. So why we need tree data structure? There may be situations where data in our programs or application is not in the linear order. There is a relationship between the data that cannot be captured by the linked list or other linear data structure. Here we need a data structure like tree. Shortly we will see that for applications that require searching, linear data structure are not suitable. We will focus our attention on binary tree. So what is binary tree? A binary tree is a finite set of elements that is either empty or is partitioned into three disjoint subsets. The first subset contains a single element called the root of the tree, and the other two subsets are themselves binary trees called left and right subtree. Each element of a binary tree is also called a node of a tree. Here is the graphical representation of a binary tree, in which there are 9 nodes and the node A is the root node of the tree. Node A is further divided into two parts, left subtree and right subtree. Left subtree consists of node B, D, E and G. Right subtree consists of node C, F, H, I. According to the definition, a binary tree is either empty or divided into three disjoint subsets. We have made three parts of a tree. Part 1 is a root node, that is A, and then part 2 is a left subtree and part 3 is a right subtree. The left subtree of node A is also a tree, in which B become the root node of the tree, D become the left subtree, and E and G become the right subtree. On going one step down and considering the right subtree of node B, we see that E is the root and its left subtree is the single node G. And there's no right subtree of node E, or we can say that its right subtree is empty. Now the left subtree of node E is the single node G, and the node G can consider as a root with empty left and right subtree. Now if we carry the same process on the right subtree of root node A, here C will become the root node, there is no left subtree is empty and its right subtree made up of three nodes F, H and I. The definition of tree is recursive in nature. This is due to the fact that the definition that we have applied on root node A is also applied to its subtree one level downward. Similarly, as long as we go downward in the tree, the same definition is used at each level of the tree, and we have seen three parts: root, left, and right. Now, if we apply the same recursive definition on the level below the node C, now the right subtree of node C will consider as a tree, and the root of this tree is the node F. The left and right subtree of root node F are the nodes H and I. So we make tree or draw tree by joining different nodes with line, but we cannot join any nodes whichever we want to each other. Consider this example. This structure is not a tree. It is due to the reason that in a tree there is always one path to go from root node to a node. In this figure, there are two paths to go to node G from root node A. This structure may be a graph but not a tree. Similarly, if we put other links between different nodes, then the structure thus developed will not be a tree. This figure is also an example of a structure that is not a tree. There are multiple links between the different nodes. For example, between node A and B, there are two links. This structure is also not a tree because there are multiple links between node B and E and F. Let's discuss the terminologies of a tree that we are going to use in our algorithms. In this tree, A is a parent node, B and C are left and right descendants or child. We're going to use three terminologies: parent, child, or descendants. The nodes that has no left or right subtree or left or right child are the leaf nodes of a tree. In this tree, D, G, H, I are leaf nodes. There is a version of a binary tree called strictly binary tree. A binary tree is said to be a strictly binary tree if every non-leaf node in a binary tree has non-empty left and right child. We know that a leaf node has no left or right child. Thus the node D, G, H and I are the leaf nodes. So we are left with a non-leaf node that are A, B, C and F. So according to the definition of a strictly binary tree, this non-leaf node must have left and right subtree. The node A has left child B and right child C. The node B has its left and right children that are D and E. But the node C has right child F but no left child. So we're going to add a left child of node C, that is node J. Here C has its left and right child. Now if we see at node F has its left and right child that are H and I. Now the last non-leaf node, that is E, has its left child G but no right child. So we are going to add another node, that is K, as the right child of node E. Now this tree is a strictly binary tree because all the non-leaf node now have non-empty left and right subtree. Level of a binary tree node. Root has level 0. Level of any other node is 1 more than the level of its parent. And the depth of a binary tree is the maximum level, that is of any leaf in a tree. In this figure, node A is a root node of a tree, so it has level 0. Node B and C has one more level than its parent node, that is 0 plus 1 is 1. So node B and C is at level 1. Similarly, node D, E, F is at level 2. Node G, H and I is at level 3. There is another version of a binary tree, that is complete binary tree. A binary tree that is a strictly binary tree and all its leaf node at level D is called a complete binary tree. What is level D? Level D is the depth of a tree. What is the depth of the tree? The maximum level of a tree is the depth of the tree. In this tree, the maximum level is 3, in which all the leaf nodes at level 3 or at level D. So this tree is a complete binary tree. If a tree is a complete binary tree, then we can find out the total number of nodes at each level. For example, level A is node A is at level 0. So 2 power 0 is equal to 1. So there is only one node at level 0. Similarly, the level 1 has two nodes. How to compute total number of nodes? 2 power 1. 2 power 1 is equal to 2. So there are two nodes at level 1. Let's find out total number of nodes at level 3. 2 power 3 is equal to 8. So how many nodes are at level 3? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 nodes at level 3. So that's how we can compute the total number of nodes at each level in a complete binary tree. At level k, there are 2k nodes. So now we can calculate the total number of nodes in a complete binary tree of depth d by adding the number of nodes at each level. This can be written as the following summation: 2 power 0 plus 2 power 1 plus 2 power 2 still 2 power d. D is the maximum level of a tree. So we will get the formula 2d plus 1 minus 1. In a complete binary tree, there are 2d leaf nodes and 2d minus 1 non-leaf or inner nodes. Let's solve an example. If we know the depth of a complete binary tree, then we can find out total number of nodes in that tree. If the depth of a tree is at 4, then it will be calculated as 2 power 4 plus 1 minus 1, that is equivalent to 2 power 5 minus 1. 2 power 5 is equivalent to 32. 32 minus 1 is equal to 31. So there are total number of 31 nodes in a complete binary tree of depth 4. We can also compute the depth of a complete binary tree if we know total number of nodes. The depth of a complete binary tree built using n node will be log base 2 n plus 1 minus 1. Suppose we have 1 lakh node, it means that the value of n is 1 lakh, reflecting the depth of a tree will be log base 2 1 lakh plus 1 minus 1, which evaluate to 20, so the depth of a tree is 20. In other words, the tree will be 20 level deep.